So, we have gone through the fundamentals of heat transfer, the different modes of heat transfer, conduction, convection, radiations, their special characteristics and so on. The first part of this course will be devoted towards understanding conduction, deriving the relevant equations and how those equations can be applied in for specific practical applications. One of the fundamental relations which is quite common in conductive heat transfer, we have spoken about this Fourier's law of conduction, which defines the material property, the thermal conductivity, and where we have seen that the heat flux, which is a vector, is proportional to the temperature gradient, and the proportionality constant defines the thermophysical property K. But the use of this equation for a control volume will give rise to an equation where the temperature can be expressed as a function of spatial coordinates, like what is the temperature at a specific x, y, z coordinate in a fixed coordinate systems, as well as what is the time rate of variation of temperature at a specific location. So, this heat diffusion equation, which we are going to derive today, would allow us to find the temperature at any temperature as a function of time and x, y, z. So, space and temporal variations of temperature can be obtained if we can solve the equation, the governing equation that can be derived based on Fourier's law of conduction. In order to do that, in order to derive the equation, the first thing one has to do is define a control volume. As we discussed before, the control volume has a fixed mass and it is defined by control surfaces. The control surfaces do not have any mass of their own. So, the conservation equation which is applicable for a control surface would simply be equal to in is equal to out. So, control surfaces do not have any mass of their own, whereas the control volume will have a specific mass. So, the conservation equation for a control volume would be rate of heat in minus rate of heat out of the control volume plus the rate of heat generation inside the control volume is equal to the time rate of change of energy stored inside the control volume. So, this generation of energy can be by nuclear means, a nuclear reaction is taking place in the inside the control volume. It can also be due to ohmic heat, due to Joule heating, some amount of energy is generated inside the control volume. So, rate of energy in, rate of heat in this case in minus rate of heat out plus rate of heat generation inside the control volume, the algebraic sum of these three must be equal to the rate at which energy is stored inside the control volume. So, we will specify a control volume, define a control volume and write this conservation equation. The physical description of the equation is going to be written in mathematical form, which would ultimately give rise to the governing equation for heat conduction in a solid. And once we have this equation, we would see what are the simplifications that can be made to this equation, and under those simplifications and with the help of appropriate boundary conditions, which we will discuss next, what are the special form of equation for temperature distribution that can be obtained inside the control volume. Because the main aim of any conduction analysis is to obtain what is the form of the temperature profile, what is the temperature profile. Because once we have the temperature profile, for example, let us say T as a function of x, then we can find out by simply differentiating the profile what is del T or dt dx at a specific location. If we know what is dt dx, multiplying that with minus k, k being the thermal conductivity, we would be able to evaluate what is the heat flux at that location. So, it is of paramount importance to know what is the temperature distribution inside, let us say, a solid at a given condition. So, the derivation, the understanding of the derivation of heat diffusion equation is what we are going to try in today's class based on a defined control volume of dimensions del x, del y and del z, where these del x, del y and del z are small scales of length which together define a control volume. So, we will assume that it is a cuboid which is defined by the length scale del x, del y and del z, and we would see how the heat comes into the system, goes out of the system, what is the rate of heat generation, and the sum total must be equal to the time rate of storage, time rate of change of energy storage inside the control volume. So, let us look at this picture, which essentially tells us this is my cuboid which has a length of dx, dy and dz. So, therefore, this is the x direction, this is the z direction and this is the y direction. So, this is at this location is x, y, z, and the top obviously is going to be x plus dx, y plus dy and z plus dz. So, this point is x plus dx and so on, and we would assume that q x is the amount of heat which enters the control volume and it leaves from this phase as q x plus dx. So, q x denotes the amount of conductive heat flow to this control volume through the surface at x. So, the surface at x has an area equal to del x, del y, del z is the area of surface x. Similarly, the y face which is perpendicular to the y direction has an area equal to dx times dz, and the z face which is the area under at the bottom, it will have an area of del x and dx and dy. So, the by x face or y face or z face, we mean that it is the area which is perpendicular to the direction mentioned. So, the area x face is perpendicular to the x direction and the amount of heat flow to the system would be denoted by qx. So, we are going to write the energy equation with the conservation of energy for this control volume. So, in order to do that, the first thing that we would do is we have to express q x plus dx, that is the amount of energy which leaves the x phase as the amount of energy which comes in to the x phase plus the change of energy in the x directions, change of conductive heat flow in the x direction with x multiplied by dx. So, this is a fundamental expression which is obtained by the Taylor series expansion of qx and neglecting all higher order terms. Now, if we see what is if we understand that dx is quite small, then a Taylor series expansion of qx around x and neglecting the terms higher order, neglecting the higher order terms is admissible, it's accurate, and therefore, qx plus dx can simply be expressed as qx plus the rate of change of qx with x multiplied by the length scale which is dx over here. So, this analysis is only valid if dx is small, which we have assumed to be small at the very beginning when we have defined our control volume. So, this form of qx plus dx is therefore definitely valid for this specific case. Once we write qx plus dx, I should be also able to write what is qy plus dy and qz plus dz exactly using the formulation that we have done for qx plus dx. So, let me write that and then I am going to write the conservation equation. So, your qy plus dy would simply be written as, using the Taylor series expansion, and q z plus d z would be equals q z plus del q z del z times d z. Okay. So, this is the first thing, which these are essentially conductive heat flow to the control volume. Secondly, let us assume that q dot is as the rate of energy generated inside the control volume. And as I have mentioned before, inside the control, as I have mentioned before, this could be for various reasons, from electrical heating to nuclear heating and so on. So, therefore, the total rate, total amount of energy generation, this is per unit volume. So, energy generation all rate, this must be equal to q dot times dx dy dz, because together this is going to be the volume. So, therefore, if q dot is the rate of energy generated per unit volume, then the total amount of energy generated, the rate of energy generation, would simply be equal to q dot times dx dy dz. And the last thing which remains is energy storage and energy storage would simply be equal to E dot, the dot denotes the time rate, would be rho Cp times dx dy dz multiplied by del t over time. So, this gives me the energy storage, the change in energy inside the control volume as a result of conduction would simply be equal to mCp delta t. And if I take the if I take try to find out the rate of energy storage inside it, then it is simply going to be rho Cp multiplied the volume multiplied by del temperature over del time. So, these terms together, so this is going to give me the total amount of heat, conductive heat, which is coming to the control volume. This is going to be the total amount of energy generated inside the control volume, and the third term will give us the time rate of change of energy storage inside the control volume. So, if we think of the energy conservation equation, the rate of energy into the system, which would be q x, q y and q z, and the rate of energy going out, which would be q x plus dx, q y plus dy and q z plus del z, plus the amount of energy generated inside the system, which is E dot g, which should be equal to q dot, which is the energy generation rate per unit volume. So, q dot multiplied by dx dy dz. The algebraic sum of all this must be equal to the time rate of change in energy storage inside the system, which is the last term that we have written. So, this equation I am going to put together now, taking into account all the in and out terms, and the conservation would give me the conservation equation with appropriate steps would give me the energy equation. So, let us see how this is done. So, with the terms which are already written before, I am going to say that rate of energy in plus rate of energy generated minus rate of energy out is equal to the time rate of energy stored inside the control volume. So, it would be Qx plus Qy plus Qz, which essentially is the in plus q dot dx dy dz minus the, so this is the generation term should be equal to energy stored, which is rho Cp del temperature by del time times dx dy dz. So, this is the equation, and when I put in for q x plus dx or q y plus dy or q z plus dz, if I put this term, then the q x over here and the q x over here would cancel out, and only this term will remain in between this and the and q x plus dx. Similarly, between q y and q y plus dy, this would be cancelled and only this term will remain, and same for q z. So, once we do that simplification, that means once I plug in the expressions of these three and combine with them, what I would get is the final equation as minus del cube x by del x times dx minus del q y by del y times dy minus del q z del z dz plus q dot dx dy dz is rho Cp del this term. Okay. We also understand this from Fourier's law. From Fourier's law, I can write that Qx is minus k times area, which is dy dz times del t by del x. So, this is the area. Q is minus k a dt dx, and since we are talking about x phase, it has area of dy dz. Similarly, q y would be minus k times dx dz del t del y, and q z would be minus k dx dy times del t del z. So, once these are put in here and you divide both sides, so and this is put in here and you divide both sides, what you would get is del x of k del t del x plus del y of k del t del y plus del z of k del t del z plus q dot is rho Cp del temperature by del time. So, this is one of the forms, one of the more general forms of the heat diffusion equation. And if you look closely, it gives you the variation of temperature with x, y, z and time. And this is nothing but the conservation equation, energy conservation equation, where the only way, only mode of energy transport is by conduction. This q dot is the energy generated per unit volume, and this is simply temperature, rho is the density and Cp is the heat capacity of the system that we are dealing with. If k is a constant, that means it is not a function of x, y and z, that means the system is isotropic, and by isotropic I mean that the system properties do not change with direction. which is true for many of the common systems that we deal with, but for some special crystals and so on, and especially when the system size is reduced, this k can be a function of the direction. So, but if we assume that it is an isotropic system, which many of the systems that we would deal in our practical studies on heat transfer, they are. So, therefore, this k can be taken out, is not a function of x, y and z, and therefore, the k can be taken out of the differentiation sign, and what we get is the most common form of heat diffusion equation, which would simply be k times del 2 t del x square plus del 2 t del y square plus del 2 t del z square plus q dot is rho Cp del temperature by del time. So, this is probably the more common form of heat diffusion equation that you would encounter. So, this simply says that it is an isotropic medium, and therefore, you do not have any variation of k with either x, y and z. A slight rearrangement gives a form of this equation, which is there in the textbook, del 2 t by del x square plus this term rho Cp by k, or rather the inverse of this term is called alpha. So, alpha is simply k by rho Cp, and if you put the units of k, rho and Cp in here, you would see the units of alpha are simply equals meter square per second. So, what this tells me is that this k, this alpha is known as the thermal diffusivity of the system. If you would probably read later on is for the mass diffusivity, which is denoted by DAB, which is the diffusion coefficient of A, and in B has also units meter square per second. So, this DAB, which is more commonly we call as only diffusivity, this is simply the mass diffusivity, but here we have a quantity which also has meter square per second, and that is why it is known as thermal diffusivity of this system. In the same way, diffusivity tells us how fast a species molecule will travel from one point to another. So, higher the value of diffusivity, the faster it would travel to a given location, given location. And similarly, the thermal diffusivity, we would see that thermal diffusivity would also tell us how fast a temperature front will propagate through the solid to reach another point far from the original point. So, conceptually, the thermal diffusivity and the mass diffusivity are going to be the same. And you probably recollect that in fluid mechanics, you have seen that mu, the viscosity divided by rho, which is the density, this mu by rho also has units of meter square per second, and this mu by rho is known as the momentum diffusivity. So, what you would get are three diffusivities which you would see in one for the case of momentum transfer, which is mu by rho. The other is the case of thermal, the energy transport, it is k by rho Cp, and the third one is the more common, the one which you commonly come across is the mass diffusivity, which is denoted by DAB. The units of all three quantities would be meter square per second, and the same units for these three quantities would lead to the unified treatment of heat, mass and momentum transfer that you would come across in transport phenomena course in your later years. But the fact that all three have the same unit would possibly have led people to think that it is possible to use the same type of analysis for heat, mass and momentum transfer. So, the fundamental equation which we now then have for conduction is this. So, this is known as the heat diffusion equation. And this specific form is for constant thermal conductivity system. Now, many simplifications to this equation are possible. For example, if you assume that the heat conduction is taking place in a system in which you do not have any heat generation. So, this q dot term would simply be equal to 0. If you assume that this system is represents a system at steady state, and by steady state I mean that the temperature is could be a function of x, y and z, but it is not a function of t. So, at steady state this temperature change with time would simply be equal to 0, and you will be left with only the 4 terms on the left hand side. What is the simplest possible situation that you can think of? That it describes the heat diffusion equation. Let us say it is being applied to a case where you have only one dimensional conduction with no heat generation and it is at steady state. So, that is the simplest possible thing which you can think of, which would give you that t is not a function of y, t is not a function of z, there is no q dot present in the system and t is not a function of time. So, if that is the case, then I will only have this term present in it, and I do not have to write the partial sign, since t is a function only of position. So, the governing equation for such a case would simply be d2t dx square equal to 0. So, this would be this, if you solve this equation, then t is a linear function of x. So, if in a solid let us say t is a function of x only and it is at steady state and no heat is generated in the system, then for that special case you are going to have a linear distribution of temperature inside the system. The same type of equation can also be derived for the case of cylindrical systems and spherical systems. So, in cylindrical systems the temperature can be a function of radial location r theta or axial location z. So, t is going to be a function of r theta and z, and in this case of spherical systems the t can be a function of r theta and phi. So, these two equations in spherical and in cylindrical coordinates are available in your text. Since the geometry is slightly more complicated for the case of spherical and cylindrical systems, the heat diffusion equation that you see for spherical and cylindrical systems do look more complicated, but fundamentally there is no difference. They only use conservation of energy to explain the physics of the system when only conductive heat transfer is present in a system. So, what we do next is, whenever you have a governing equation like the way we have seen for the case of one dimensional steady state conduction with no heat generation, my aim is to obtain, as I have said before, to obtain t as a function of x, y, z and time. So, whenever you are integrating, whenever you are solving the governing equation, you are going to get integration constants, and the integration constants can only be evaluated if you know what is the boundary condition. So, we would see in the next class what are some of the pertinent boundary conditions which are commonly encountered in conductive heat flow, and how with the use of appropriate boundary conditions we would be able to obtain the temperature profile inside a solid undergoing conduction. So, in this class, from first principles from energy generation, energy conservation equation, we derived what is known as the heat diffusion equation. And we have done it for Cartesian coordinate systems. It can also be done for cylindrical and spherical coordinate systems. We have also seen that simplification of the equation can lead to several conditions, several situations where in some cases it would be possible to solve the equation with boundary conditions that we would see in the next class. And this also shows us that this k by rho Cp, this defines a new property of the system incorporating the rho, the density, the specific heat and the thermal conductivity. So, the progression of temperature front inside a solid depends not only on the thermal conductivity, it also depends on its specific heat and density. So, together they define a thermal diffusivity which would tell us how fast or how slow a temperature front will move into a solid object undergoing conduction. So, that way it is similar to mass diffusivity, and we have seen in fluid mechanics that we have something called momentum diffusivity as well, which would be an unifying, the start of an unifying concept between heat, mass and momentum transfer. So, we will stop here today, and in the next class we will start with the relevant boundary conditions and the solution of heat diffusion equations.